the Lagrange error bound. So this problem says let y equals f of x be the particular solution to this differential equation. That means this is the derivative of the function f of x, but notice it has x and y in it, and it goes to this point, 4, 1. So there's 1 point on the original function. And then it asks us to write the second degree, so that means the highest exponent is 2, Taylor polynomial for f about x equals 4. So there's our center. Notice this one's not a Maclaurin one, because the center is not 0. And then we'll use the Taylor polynomial to approximate f of 4.4. But first we have to write that polynomial down. So let's get the pattern started here. So remember we have the 0th derivative, which is the original function, and we plug in the center, which in this case is 4, times x minus the center, x minus 4 to the 0 over 0 factorial. And then plus, then it's the first derivative, f prime of 4, x minus 4 to the first over 1 factorial, plus, then it's the second derivative of 4, x minus 4 squared over 2 factorial. So we stop right there because it's second degree, refers to the highest exponent of the x is now 2. So now we can start substituting what we know. F of 4 they give you is 1 right here. So we can substitute that in there. X minus 4 to the 0 is also 1. 0 factorial also 1. F prime of 4, well, that's the first derivative of 4. So normally we would just plug in x equals 4, but here notice our derivative has x and y. So those go together right here, so we can substitute them both in to find the value of the derivative when x is 4. So the way you'd write that, the derivative specifically when x equals 4, and the corresponding y coordinate is 1. So they give you 2 times y, which is 1, plus x, which is 4, gives you 6. So that'd be 6, x minus 4 to the first is just x minus 4 over 1 factorial is just 1. Plus, now we need the second derivative of 4. So that we don't have yet. So that's where you have to use implicit differentiation, since this is not a function. Because the x's and y's are mixed up in there, and take the derivative of the first derivative to get our second derivative. So our second derivative, d squared y dx squared. Well, the derivative of 2y would be 2, but remember every time the variable doesn't match up with the x here, you have to multiply by dy dx. Plus the derivative of x is just 1. So if we needed to get the second derivative in terms of x and y, which sometimes you do, then we would have to substitute in 2y plus x in for x. Sorry, in for dy dx. And you could still do that here. But this one's a little simpler because we just need to know what the value of it is specifically at 4. So you can actually substitute in right now. Specifically when x equals 4 and y equals 1. And the reason why you're able to do that is we already know from right here the value of the first derivative at this point is 6. So we can substitute then first for the dy dx plus 1 gives you 13. So that's what the second derivative for is, 13 times x minus 4 squared over 2 factorial is just 2 times 1, which is 2. All right, so let's write out what we have here. So our second degree Taylor polynomial. So you could write t sub x equals, first term is just 1, plus times x minus 4 plus 13 over 2 x minus 4 squared. All right, so that's the first thing that's for. There's our second degree Taylor polynomial. And now we're going to use this to approximate f of 4.4. So now we just plug in 4.4 in there. for the x's. And then we can just simplify that. All right. So we get 1 and then 4.4 minus 4 is 0.4. And you can work with decimals or fractions, whichever you prefer here. But usually when you're doing this without a calculator, fractions tend to be a little easier to work with in general. So now I look for these 0.4 to fractions. So 0.4 is 4/10, but 4/10 reduces to 2/5. It's also 2/5 squared. So that would give you 6 times 2, 12/5. Two squared gives you 4 over 5 squared is 25. And you can do a reducing on this last term here. 2 goes into 4 twice. So our third term is 2 times 13, 26 over 25. So we can just get a common number of 25 here. So you multiply this one by 5 over 5. 5 times 12 is 60. So it would be 60 over 25. And 1 just multiplied by 25 over 25. Multiply by 25, so you get 25 over 25. So we get T2 of 4.4 equals, see, 20 plus 20 is 40, plus 60 is 100, 5 plus 6 is 11, so that's 111 over 25. So that's what the Taylor polynomial gives you, so that's our approximation for f of 4.4. F of 4.4 is approximately equal to 111 over 25. All right, now let's take a look at part B. It says now that the third derivative is less than 30. For 4 to 4.4, so that's the where our Taylor was centered, and that's where our approximate is on that interval. And then it says use the Lagrange error bound to show that the approximation from part A differs from the actual value by less than 0.33. All right, so we'll see another way we can write the Lagrange error bound. So you can write, since we used a second degree one, you can use R of 2. But another way that this can be written, which is what the wording here is using, is the absolute value, because the error is always positive. It could be under or overestimated by this much. And that the way you can write this is the actual value is f of 4.4. That's the true value. The differs, that's like minus. Our approximation was t sub 2 of 4.4. Okay. So that's less than or equal to. And then, so this is the actual value. This is our approximation. And then since it's the second degree, it's one more than that. So it's the third derivative of where we're approximating 4.4. And then we're approximating 4.4 minus the center is 4 to the third over 3 factorial. So the third derivative, it tells us right here, is less than 30. So that's the maximum value. Remember on this one, you can't always find the exact value, so you want to put in what the maximum is. So it can't be more than 30. So you put in 30 right there. And then again, 4.4 minus 4, that's 0.4 to the third. 3 factorial is 3 times 2. All right, so we can start to reduce this here. That is 3 goes into 30, 10 times. And again, let's write that 0.4 as a fraction. It'll be a little easier to simplify. So we've got 10, and then that's 2 fifths. 4 tenths reduces to 2 fifths cubed. Oh, actually, you can reduce it further, huh? The 2 goes into the 10. 5 times. So now we just have 5 out in front. So 5, and then 2 cubed is 8 over 5 cubed is 125, and then 5 goes into that 25 times. So we've got 8 over 25. And we need to show that's less than 0.33. So this is in hundredths, so we need to convert this to hundredths. So you have to multiply by 4, so that's 32 over 4. Which is less than, 32 over 100 when you multiply by 4, which is less than 33 over 100. So the way you can write that is our approximation here, f of 4.4, the actual value minus our approximation. Less than or equal to 32 hundredths, which is less than 33 over 100. So you do have to simplify it down so you can actually tell that it's less than that value. And that concludes the notes for AP Calculus on the topic of the Lagrange error bound.